We will never reach Mars. We know how that sounds. We have landers there already. We have plans, flight tests, and countdown clocks. We can draw the transfer orbits with confidence. But when we say reach, we don't mean touch the dirt, plant a flag, and stream a victory speech. We mean arriving in the way our myths demand. Safe, self-sustaining, ordinary. We mean a second home. And on that definition, physics has been whispering the same answer for decades, an answer that comes from a place you'd never expect. In a moment, black holes will explain why. Before we dive in, let's be clear about the claim. Never reach Mars does not mean no human will ever set foot there. A crewed landing is within reach. A research outpost for months, even a few years, is plausible with focused effort. We're not saying rockets can't fly, nor that courage or ingenuity have limits we've already hit. We're saying something narrower and somehow bigger, that a stable, open-ended, self-sufficient Mars civilization, the story that makes Earth optional, collides with limits we can't negotiate away. Limits of energy, of heat, of radiation, of reliability in harsh environments, and a quieter limit that modern physics has been circling for decades, the way information and entropy are accounted for at the edges of things. When we say reach, we mean cross those boundaries and stay there without leaning forever on Earth's shoulder. That version of Mars is farther away than distance suggests. To see why, it helps to rewire our intuition. Think about temperature: hot, cold, warm. It feels basic. But temperature is a summary, an emergent property of trillions of molecules rushing, colliding, and vibrating. We don't calculate each collision to decide whether to wear a jacket. We use a higher level story that hides details we don't need. Emergent doesn't mean fake. It means real at the scale we live by, built on deeper rules we rarely notice. Now think about a map. Have you ever stared at a subway map that squashes real distances to reveal connections? The territory isn't distorted underground. Your representation is, in a way that's useful. Space can be like that. The line from Earth to Mars on a textbook diagram looks simple. 8 months by rocket if you catch the right window. The map is helpful. But the map hides something essential. The exchange rates we must pay to move life across that line: calories, oxygen, error margins, maintenance, waste heat, radiation shielding. The map hides how reality charges us for the edges. Or consider your phone's home screen. Simple icons, smooth gestures. Beneath, there's an operating system, drivers, memory management, physics inside semiconductors. Your daily life runs on a user interface evolved to keep you moving quickly without requiring you to inspect transistors. Our everyday intuition is like that for Earth. It's a UI tuned by evolution for blue skies, thick air, 1G of gravity, a magnetic shield, sunlight filtered by an atmosphere, and a biosphere that quietly keeps entropy at bay. When we leave, we're not just changing scenery. We're leaving our native interface and handing ourselves over to raw physics. Raw physics can be surprisingly uncooperative. At small scales, quantum objects refuse to be little billiard balls. They blur and entangle. At high energies and on cosmic horizons, gravity entangles itself with information in ways we only partly understand. We had to build a new mental map to avoid wrong turns. The Mars story needs the same humility. The classical cinematic picture point, a big rocket fly, unload a city, is an interface illusion. The true costs live somewhere else. Pause the narrative and run a thought experiment. Imagine a submarine that never surfaces, every breath recycled, every gram of waste tracked, every degree of heat dumped into the ocean with meticulous care. Now remove the ocean. Put that submarine into vacuum with only radiators to throw heat into the cold. Strip away the easy out. That isn't a mood, it's the physics of life away from Earth. Keep that image in mind, because this is where black holes come in. Black holes taught us a shocking lesson. Information matters more than we thought. Stephen Hawking showed that black holes radiate. It looked for a while like they might destroy information, erasing the details of everything that fell in. Physicists like Leonard Susskind fought that idea, arguing for a universe where information isn't lost. The battle reshaped our understanding. The punchline was stranger than anyone expected. The information content of a region doesn't scale with its volume. It scales with the area of its boundary. The entropy, the measure of how many internal states are possible, goes with the surface, not the inside. Sit with that area, not volume. From that seed grew the holographic principle, the idea that in certain spacetimes, everything happening in a volume can be fully described by degrees of freedom living on a lower dimensional boundary. The inside is, in a deep sense, encoded on the edge. Why bring this to Mars? Not because Mars is a hologram we can hack, but because black holes forced us to accept a radical accounting rule. The boundary may quietly decide what's possible for the interior. And in the gritty engineering of living in space, the same rule shows up with cruel clarity. Between planets, high-energy particles, galactic cosmic rays, and solar storms slice through flesh and circuit boards. On Earth, a thick atmosphere and a magnetic field do the work of deflecting and absorbing. In a spacecraft or a habitat, the job belongs to your skin, metal, water, polyethylene, or regolith, shielding lives on the boundary. And shielding is mass. Mass is fuel. Every extra centimeter of water or plastic you add to stop heavy ions forces your launch system to carry more propellant, which demands more structure, which demands more propellant. The loop tightens like a knot. Now take heat. Everything alive produces waste heat. So do pumps, lights, processors, and chemical loops. On Earth, air and water convect heat away without complaint. In vacuum, there is no convection, no breeze. You radiate heat as light, and the rate at which you can do that scales with surface area. Meanwhile, your life and work, the sources of heat, scale with volume. Build a thriving little city, and your heat bill grows faster than your radiator skin can pay it, unless you keep extending those wings of finned, fragile panels, the edge again, and take pressure. You need a stable pressure envelope to breathe. Every seam, every window, every valve is a failure mode on the boundary. Micrometeoroids don't care about your schedule. Dust grinds into seals. The difference between a livable interior and a vacuum is measured in millimeters of material at the edge. So when people say, we'll just scale up, we should ask them to draw the edge and price it. Doubling the population doesn't just double food and water, it doubles waste heat. It squares the maintenance workload because the web of interactions, air loops, CO2 scrubbers, pumps, farms, filters, spare parts grows denser, and the systems you add to handle complexity add their own complexity. It's like error correction. In a noisy channel, you add redundancy to make the message reliable, and the overhead grows until it dominates the message itself. The physics of the edge doesn't care how stirring the soundtrack is. We can come down from orbit for a moment and talk about Mars itself. Mars has some atmosphere, but it's thin. It slows cosmic rays a little and soaks up some ultraviolet, but not enough to make outdoor life gentle. There's no global magnetic field. Dust storms can dim the sun for weeks and spread planet-wide. The dust itself is electrostatically sticky, abrasive like powdered glass, and likely laced with perchlorate salts that complicate agriculture and corrode equipment. Seals wear, bearings fail. Panels lose output as powder cakes on. On Earth, rain falls and winds scour. Terrain breathes and recycles. Mars is patient. It accumulates entropy. And then there's time. Messages from Earth take 3 to 22 minutes to make the trip, depending on the geometry. You can't joystick a crisis. You can't call home for a real-time fix. Your Mars operation must carry the information it needs: autonomy, training, procedures, and tools to solve novel problems without waiting for instruction. Information has mass only when it's stored in metahumans, drives, servers, and in space. All of those produce heat and fail with time. Again, the edge, to keep coherence, you keep paying at the boundary with redundancy and repair. At this point, it's fair to ask what is settled and what is speculation. Settled. The rocket equation's exponential penalty for adding mass, the reality of galactic cosmic radiation and solar particle events, the difficulty of radiative heat rejection in vacuum, the inherent delays of light speed communication across interplanetary distances, the empirical fragility of complex closed life support systems, which on the International Space Station demand constant maintenance and resupply, also settled within their proper domains. Black hole entropy scaling with area and the broader holographic intuition that nature often counts states at the boundary, speculative but useful as intuition, treating the boundary constraints of space habitats as the everyday echo of those deep area laws. We're not claiming there's a literal black hole in your cargo bay, we're noticing the rhyme. If you want a more precise example of how the inside can be a story told by the edge, theoretical physics has built one. It's called ADS CFD anti-de Sitter conformal field theory correspondence. It's a technical mouthful with a simple spirit. In a certain kind of curved spacetime, the entire bulk with gravity is exactly equivalent to a quantum theory without gravity that lives on the boundary. The inside is not fundamental there. It emerges from entanglement and dynamics on the edge. Our universe is not exactly that spacetime. So we shouldn't take AdStift as a blueprint, but it is a laboratory where we can watch geometry and gravity emerge from information. It shows mathematically that connectivity, how entangled pieces of a system are, can weave a space. More connectivity, tighter fabric, less, looser. Translate carefully and metaphorically. If we want Mars to be close, the priority isn't only bigger rockets, it's thicker connectivity. It's saturating the Earth-Mars system with robust, redundant, error-corrected flows of information, high-bandwidth lasers, cached libraries, on-site training, autonomy that handles 99% of problems, and people who can invent the missing 1% on the spot. In that view, reaching Mars isn't about moving a million bodies quickly. It's about moving understanding. Atoms relocate when they must. Bits move always. Here's a thought experiment to press the point. Imagine we could send either one of two payloads, 1,000 tons of pre-built habitat hardware, or 1,000 terabytes of manufacturing recipes, digital twins, fault trees, self-repairing designs, and training sims that let modest hardware already there reinvent itself again and again from local resources, which reaches farther. History is unambiguous. In most domains, the economy of bits outruns the economy of atoms. It's ADS CFT's lesson in civilian clothes. When the edge is powerful enough, the interior can be conjured on demand. None of this denies the romance of going. It refocuses it. The constraints are not moral judgments. They're the scorekeeping rules of a universe that, at multiple levels, puts fate on the edge. Let's catalog the edges we'd have to master for Mars to stop leaning on Earth. We can protect ourselves in transit by packing water, plastics, or hydrogen-rich materials around the crew quarters. We can shape tanks to double as shields. We can build storm shelters for solar outbursts. But to blunt the constant drizzle of high-energy cosmic rays, you want thickness on the order of tens of grams per square centimeter wrapped all around. In transit, that mass hurts. On Mars, you can bury habitats under regolith to use the planet itself as a shield. That's promising. But excavation is work, and machines break, and seals wear, and heavy equipment needs spares. The balance sheet never leaves the boundary. Heat next. On the way to Mars, you reject heat only by radiation. Every watt you generate must find its way to a black panel that glows in infrared. As your operation grows, the radiators sprawl. On Mars, the thin air adds a little convection. You can run loop radiators, bury pipes, use the ground as a thermal buffer. But dust coats radiators. Storms warm the air while dimming the sun. Margins shrink. Engineers can beat back any single issue. The combination is the problem. Then there's atmosphere and pressure. A livable pressure inside a dome or cylinder wants to leak out. It's a small river that never stops, testing gaskets and infiltrating cracks. Regolith dust sneaks in, grinds into door seals, sticks to suits, carries percolates into airlocks. On Earth, we can fail softly. A pinhole is an inconvenience. On Mars, the same pinhole is a trend that must be found and reversed before the inventory of air reaches a line you can't cross. Food and water. Closed ecological systems close imperfectly. You can recycle a high percentage of water, scrub CO2, reprocess waste. Plants can help, but every loop you close has a failure rate, and failure rates multiply. The IS keeps astronauts alive with a constant stream of spares, technicians, and discretionary power. A Mars base must bootstrap the same competence locally with fewer hands and less redundancy. It's the same logic as digital error correction. You can get arbitrarily reliable transmission in a noisy channel if you accept arbitrarily large overhead. How much overhead can a fledgling Mars base carry? Health and gravity. We do not yet know whether 038G, the gravity on Mars, is enough to prevent the bone loss, muscle wasting, and fluid shifts that plague bodies in orbit. Spin gravity is a straightforward solution in principle. Build rotating habitats. But the structures to spin at comfortable radii are large, heavy, and mechanically demanding, and your edges must be stronger and more reliable. Inside a spinning habitat, the themes repeat: radiation shielding, heat dumping, pressure sealing. Every fix loops back to the boundary. Psychology and culture. Isolation, monotony, and distance distort groups. Delayed messages create asynchronous conflicts. Small groups amplify small quirks. The way to fight that is information again, training, norms, rituals, decision rule software for minds. It has almost no launch mass. But whenever culture must be restored by importing humans, new leaders, specialists, mediators, you feel the tug of distance and the cost in atoms. We've said emergent a few times. Let's pause there. In modern physics, there's a live, serious idea that space, time, and even matter might be emergent, effective descriptions of something deeper in quantum and informational. We are not claiming that as settled truth, but if it's even partly right, then going somewhere isn't a primary act. It's a macroscopic story we tell when the emergent variables behave well. On Earth, they do. On Mars and in deep space, they misbehave. Light speed delays stretch cause and effect. Harsh environments shorten mean time between failures. Our tidy narratives of progress build a village, then a town, then a city crack under a bookkeeping they weren't designed for. Plants use it to build structure. Ecosystems dissipate energy while maintaining order. The planet radiates heat away from the top of the atmosphere, which is again a boundary. Mars gets less sunlight. Its thin air and dust complicate harvesting. You must become the biosphere's engineer and its janitor forever. That's not impossible. It's just relentless. The edge you must maintain is long. Here's the reflective twist we promised early on. If the universe often ties fate to edges, if black hole entropy scales with area, if holography makes interiors live on boundaries, if spacecraft and habitats succeed or fail at the skin, then maybe the path to Mars that works is the one that respects the edge. Build the boundary first, master it. Let interiors bloom from there as needed, not as monuments. What does that look like? It could start not on the surface of Mars, but in Earth orbit and cislunar space. Build closed ecological habitats at scale, with spin gravity that can run for years with local repairs and minimal resupply. Treat their radiators, shields, and seals as first-class citizens. Make maintaining the edge an art. Let those habitats fail and be fixed. Learn which parts demand Earth's deep supply chains and which we can fabricate in orbit. If we can't keep a city alive and comfortable in orbit where help is close, why expect more on Mars where help is months away? Simultaneously, flood the Earth-Mars corridor with information. High-power laser comms, compression schemes resilient to dust and weather. Digital twins of every habitat, rover, and reactor on both worlds so problems can be simulated and solved across the gap. Send algorithms that can reroute around failures, generate checklists no one thought of, and teach novices to become experts on the fly. Let small human crews ride atop a towering base of bits. Let robots do the heavy lifting, build berms, bury habitats, dig ice, and 3D print structures from local regolith. Humans come when it matters most to explore, to repair what only hands can fix, to ask the questions that only eyes and minds in the place can ask. This isn't giving up on Mars. It's giving up on a specific picture that hides the true costs. It's accepting that the economy of bits outruns the economy of atoms when distances grow and edges dominate. It's recognizing that meaning is emergent too. A research outpost is meaningful. A rotating crew is meaningful. A robotic industrial ecology guided by human aims is meaningful. Emergent does not mean fake. You might ask, what about breakthroughs? What if we invent better propulsion, better shielding, better medicine? Yes. Every real advance helps. High efficiency electric propulsion changes transfer strategies. In situ propellant production on Mars lowers the mass you must launch. Advanced materials can make radiators lighter and more durable. New chemistries can scrub air and recycle waste more completely, but the boundary logic is stubborn. Even with better tools, the skin is where you will spend attention, mass, and time. There are also alluring shortcuts that often return to the same theme. Magnetic shielding for cosmic rays, perhaps, but making strong, stable fields at large scale around habitats is an engineering challenge that circles back to mass, power, and reliability edges. Underground habitats to use regolith as shielding? Sensible, yet now every hatch becomes a critical boundary. Nuclear reactors for steady power, useful, and they bring heat to dump, and new radiological boundaries to care for. Space is a place where edges multiply. If this sounds defeatist, it isn't. It's merely honest about the shape of the problem. The promise is there, and it's beautiful. A civilization that expands its zone of responsibility, that learns to handle its own edges with grace, that stops confusing myth with plan. In that light, we can even make peace with the title of this story. We will never reach Mars in the mythic way, but we can build something better and more durable. An Earth-Mars civilization where information and agency flow, where visits are normal, where local industry sings, where we celebrate not the size of our rockets, but the craftsmanship of our boundaries. What falls out of this view are a few implications worth holding on to. First, redefine reach. If reaching means millions of people living under domes in the next few decades, probably not. If reaching means a network that binds Earth and Mars into one system, high bandwidth communications, robotic autonomy that can improvise, local production of fuel, water, metals, and glass, periodic human crews that stay as long as medicine allows, and infrastructure that survives dust storms and setbacks, then we may reach sooner than we imagined. Reaching, on this definition, isn't a flag. It's a feedback loop that stays stable. Second, invest in boundaries. The glamour is in liftoff videos. The lifetimes are in skins. Shielding that doubles as structure and water storage. Radiators that can be cleaned, repaired, and expanded. Seals that shrug off dust. Filters and scrubbers that are easy to remanufacture on site. Pressure vessels designed to be patched by tired humans in clumsy gloves. Interfaces that reduce error, because errors add heat and waste. The culture shift is subtle. Celebrate the unshowy genius of edges. Third, colonize by bits first. Move designs, code, training, culture, move the patterns that let atoms reorganize themselves where they are. Every kilogram of local material made useful by a terabyte of know-how is a kilogram you didn't have to hurl across a gravity well. If black holes told us that information can live on a boundary and still command the interior, then our strategy should rhyme, saturate the edge with information, so that when we do move atoms, they click into place with purpose. And finally, practice emergence. Don't pretend that cities will spring up because we want them to. Let small operations accrete. Let capacities emerge: mining, refining, glassmaking, farming, medicine, each tied to sensors, procedures, and backups. Expect failure, because failure is the lab work of emergent systems. Treat resilience as a design constraint, not a last-minute add-on. If space, time, and matter are at least partly emergent, then so is civilization. Let it self-assemble from the right seeds. We began with a provocation. We will never reach Mars. Then we clarified we don't mean no footprints. We mean that the myth of a quick, easy second Earth ignores a subtler physics. We borrowed intuitions from black holes and holography, where information and possibility often live on boundaries. We applied those intuitions to the grittiest of details: radiation that demands mass, heat that demands radiators, pressure that demands perfect skins, delays that demand autonomy, and complexity that demands error correction. The pattern reappeared every time. The edge rules. This isn't an argument to stay home. It's an argument to be wiser guests. We can go, and we should. We can learn the craft of life beyond Earth without lying to ourselves about the bill. And if we do, the story we tell our children will be truer and more inspiring than the posters promised. It will be a story about mastering boundaries so thoroughly that interiors become easy. It will be a story about turning distance into a property of information, not just meters, and shrinking that distance with a civilization that knows how to talk to itself across the dark. Physicists like Leonard Susskind didn't set out to write a manual for Mars. They were doing something stranger, defending the conservation of information at the edge of black holes, and discovering that, in some deep sense, the surface can carry the weight of the world inside. We don't live in a black hole. We live in a universe where the echo of that idea shows up in our engineering every day. If we listen, it nudges us away from spectacle and towards strategy. So, will we reach Mars? If reaching means living there like here, probably not. If reaching means building a durable Earth-Mars network that trades not only materials but meaning, very likely and possibly sooner than the old dream. That is not a smaller future. It's a smarter one. When the universe ties fate to the edges, the wise move isn't to fight the skin, it's to master it. Build better boundaries, and the inside will take care of itself. If this reframed your sense of what reaching Mars could mean, you're in the right place. Subscribe for more slow, reflective dives into the physics behind our biggest stories. And tell us in one sentence, how would you redefine reaching Mars